Okay, this is section 1.3, page 17 in your textbook. Go ahead, Nicholas.
Properties of graphs and of functions. Investigate the matter. Two students created a game that they called Which Function Am I? In this game, players turn over cards that are placed face down and match the characteristics and properties with the correct function. The winner is the player who has the most pairs at the end of the game. The students have studied the following parent functions.
Okay, so there they are. You can see the 7 parent functions. Again, this should be a review for you guys. It says, which criteria could the students use to differentiate between these types of functions? All right, so there's a few definitions we're going to have on the side. We're going to go on over them. The first is the interval of increase. So it's the interval within a function's domain where the y values of the function get larger, moving from left to right. So it's important that you guys always read the graph from left to right. Okay, otherwise that can get confusing. So as I look from the left side to the right side, what happens to these y values? They go up. Okay, so in this particular parent function, the values are always increasing. Or another way of saying that is the interval of increase is from negative infinity to positive infinity. So what is the domain in which these intervals are increasing, or the y value is increasing? Well, they're always increasing in this particular graph. Okay? The intervals of increase for the graph f at x equals x squared, as you can tell, if I read from left to right, I notice from the left side to the right side, I'm initially going down till I get to 0. And then I start moving up. So my interval of increase would then be 0 to positive infinity. Okay? And counter to that, my interval of decrease is when I'm going downwards. Again, reading the graph the same direction from left to right. Okay, so my f at x equals x squared. Interval of decrease would be negative infinity over here to 0. Okay, so interval of increase when y values are going up. And it's always important to read left to right. Okay, interval of decrease when y values are going down. So using that logic then, who can tell me what my interval of increase would be for this function here? Interval of increase for the m at x equals the square root of x. Luke, what do you think? Let's look here, this graph. When are my values of y moving up?
0 to positive infinity.
Very good, yeah, exactly. They're always moving up for this particular graph, but it starts at 0, so yes, 0 to infinity. And my intervals of decrease for this graph, Joseph? Right here, where my pen is, on the screen. Nicholas?
In positive infinity down to 0.
Positive infinity down to 0. Okay, you would never use that interval the way you read it. You want to read from left to right. So you're saying from 0 to infinity. But we just found that that was the interval of increasing. So I'm asking, what are the intervals of decreasing? Gianluca? Yeah, there's none. Okay, because this graph is never decreasing. The y values are never going down. Okay, so it's a bit of a trick question. This one here, what are the intervals of increasing? Yeah, Lyndon?
From negative interval to positive interval.
Yeah, negative infinity to positive infinity. Very good, yeah. Okay, and the reason why is because it's always increasing. So Alan, the intervals of decreasing on this graph?
None?
Yeah, none, again, because it's always increasing. So this one's a little harder. The intervals of increasing. Jason?
From 0 to 90 degrees.
Good.
And from 2 270 to 360.
Very good, excellent. It actually goes past 360. It goes up to 450, right? Because this is still increasing after 360, right? But yeah, so basically you can see every time the graph is going up or the y values are going up, that's our interval of increasing. Yeah.
But how would you write that? Because aren't there an infinite amount of those like sections of 270 to 360 plus?
Yeah, so you're right. It would be tricky to write out in set notation. You could just write between these values and then dot, dot, dot. Okay? Every 360 degrees between these values. Okay? So the first one says, graph each of the parent functions on a graphing calculator and sketch its graph. State the domain and range of each function and determine its zeros and y-intercepts. So we have the sketches. I asked you guys to download a graphing app, so you guys can do this a bit later after the lesson and just plug in these parent functions and see and just confirm that you get the same graphs. Okay, the first one says, state the domain of each range. Domain and range of each function and determine its zeros and y-intercepts. So first of all, what are the zeros and y-intercepts? What does that mean? Zeros, Lyndon?
When the function crosses intercepts all the way across the point on the x-axis.
Right, so the zeros are when the y value is equal to 0, or, which is the same thing, when the graph crosses or touches x-axis. Okay, that's the zeros. The y-intercepts, of course, is when the graph touches or crosses the y-axis. Okay? So zeros have another name. Can anybody tell me what they're also called? There's actually a few of them. Yeah, Luigi.
X-intercepts?
Good, x-intercepts. So I'm going to write them here. Zeros, x-intercepts. What else? Yeah, Jonica? Roots, good. And there's one more. They call them sometimes the solutions. Okay? Those all referencing when y value is 0. Okay, so let's look at this first function here. And let's state the domain and range of each of the functions. So, this first one, we're going to put domain up here. What's the domain of this function? Marco, yeah.
Domain is equal to outer numbers, x is equal to outer numbers.
Good, yeah. And the reason for that is because we're crossing. You don't see them there, but there should be little arrows here. Okay, this graph definitely does not stop at 3 and -3. It keeps going. Okay? Goes for all of these graphs. Okay, the domain for this one. We'll do all the domains first. Lyndon, yeah.
Domain is x equals set of real numbers.
Yeah. Good, and that's because we cross all of the x values.
Do you want me to say the range as well?
No, I'll get to the range. And Luke, the domain for this one,
Which one? Sorry.
the third one.
X equals any real number.
Not quite. There is a stipulation here. David.
Oh, okay. Can equal 0.
Right. Can equal 0 because we have a vertical asymptote here. Okay, any questions about that? See how the graph diverges when it gets to x equals 0? Never touches this line, okay? So that's why it's x cannot equal 0. Domain for the next one? Yep.
X equals the sum of real numbers.
Yep. This one over here? Someone else. Alan. Domain for this one.
It's x is the set of all real numbers. But is less than zero.
Sorry, say that again.
Set of all real numbers, but it has to be greater than zero.
Greater than and equal to 0. Okay? We know it's n equal to 0 because in this case, if we sub in 0 for x, we do get a value for y. It happens to be 0, but it's still a value, so that we know x can be 0. For this one, of course, we can't get a value for y. If we sub in x equals 0, we get an unknown value for y. Daniel, this one?
Oh, just x is all real numbers.
Good. Okay, and Jonathan, this one? What values of x are possible on this graph? Hammer, can you help him out?
For which?
This one right here. The last one.
You know how you said like values, like
What are the possible values of x for this graph?
x equals all real numbers and
That's it. You're good. You're good. X is all real numbers, right? Because it crosses all the x values. Okay, Kevin, range for the first one.
For the first one, y is an element of all real numbers.
Good. In this case, you'll see in the book, in the textbook, they'll actually write this. F at x ER, okay? That's the same thing, just using set notation, right? Just replacing the y with f at x. Okay?
So would you prefer to use that or just y?
I don't care. Yep,
The second one?
yep.
So the y equals a set of real numbers, but must be greater than or equal to 0.
Good. Let's try Gennaro, the range for this third one at the top.
Y is an element of all real numbers, but it can equal 0.
Very good. And Jason, this one.
Y is an element of all real numbers, but it can't equal 0.
Why not?
Greater or equal to 0.
Sorry?
Greater or equal to 0.
Great, good. Can equal 0, it just has to be greater than or equal.
It can't equal 0?
No, it can, yeah, it's on 0 right now. The way we know that, if we plug in 0 for x, will we get a value of y? Yes, we will. Philip, this one?
Set of all real numbers. And that's it. Or greater than or equal to 0, yeah.
Yeah, and because it's above 0, right? It has to go up from 0. Yeah, next one. Lyndon?
Y must be y is the set of real numbers, but must be greater than 0.
Good. It's not equal in this case. Okay, and that's because y equals 0 is a horizontal asymptote, so it does not touch 0.
Hi, Miss Tuscany, how are you?
This is Mr. Mills.
Oh, sorry, Mr. Mills, never mind, thank you.
Finally, the last one. I don't know if you're going to say any of these is hard. This might be the hardest one. Kevin?
Y is an element of all real numbers, and 1 is greater than, 1 is equal to or greater than y, and y is less than or equal to, greater than or equal to negative 1.
Okay, good. So one way that I've kind of mentioned to you guys already how to write this is if you put y in the middle and you put the signs going that way, you can start from the bottom and go to the top. So -1 and 1. So y is less than and equal to 1, which is here, and it's greater than and equal to -1. All right, so there's our our range, our domain and range. Next, we're going to look at the zeros and y-intercepts. Okay, so this shouldn't take as long. Looking at the first one, the zeros and y-intercepts. Ramon, what's the zero and y-intercept for the first one? So we'll start with the zeros.
0.
Zeros, remember zeros is when the y value is 0, so it's always given as an x value. So what x value is y 0? So we have the zeros, x equals
0.
yeah, good. X equals 0 in this case. So when is y 0? Well, when x is 0. Okay, and then the y-intercept. Y-intercept, when do we cross the y-axis? Well, that's when x equals 0 as well. Sorry, that's when y equals 0. Y-intercept, obviously x has to be 0, so I wouldn't write it that way. The y-intercept is at y equals 0. All right, next one. The zeros. Yeah, Jesse.
X equals 0.
Good, so zeros, x equals 0. So when is the y value 0? Well, when x is 0. And it crosses also, the y-intercept is y equals 0. Okay, it also crosses at 0, 0. All right, this one a little more interesting. Zeros, so when is the y value 0 here? Yeah. When it's 1, okay, so if I go to x equals 1, I don't have y equals 0, I have y equals 1 there. Marco?
N equals 0. This is a mechanical.
Yeah, so we would say here for zeros, we would say there's none. Okay, there's no point on this graph when y is 0. Okay, it never touches the x-axis. The y-intercept. Okay, you can put your hand down. You've answered enough. Okay, Alex.
Actually, isn't there no y-intercept?
Right. Yeah, there's none as well. Okay. The 0 for this graph, Kevin, or yeah, Kevin. This one right here. What's the 0? So when is the y value 0?
At x equals 0.
Yeah, you're right. I was asking that, Kevin, but you're right. Yeah, x equals 0. And the y-intercept over here, Kevin? Sorry? This one right here. When do we cross the y-axis?
At 0, 0.
Yeah, so the y-intercept is when y is equal to 0.
So say if x cannot equal 0, then y is also can't equal 0?
No, it depends on the graph. If it crosses through 0, 0, that's the case, yes, but not always. Okay, we're going to see that coming up. This one, these zeros are, what's the 0 on this one? Jason?
X equals 0.
Good. Just finding that's a repeating theme. And y is equal to 0 again. There's our y-intercept. So y-intercept and zeros. Okay. Next one here. This one's a little different. Luke, what's the zeros for this one?
The only 0 would be. There would be no 0.
Good. There's no zeros. Why is that, Luke? Why is there no zeros?
It's exponential.
No.
And it doesn't start with nothing.
No, it's just simpler than that. Yeah, it never touches the x-axis. It can be exponential, but if we translated this 2 down, right, it would definitely have a 0, right? It would cross through. Okay, so it's still an exponential function, just translated down. And the y-intercept for this one, David. Good, y equals 1. How could I find these values if I don't have the graph? Like, we're getting all these answers by looking at the graph. What if I just had this? How can I find out the y-intercept and the x-intercept now? David?
For the y-intercept with a 0 to x.
Good. So to find y-intercept, you plug in x equals 0 to equation. Okay, so we would have y equals 2 to the power of 0, which is equal to 1. Y equals 1. All right. To find the zeros, we plug in y equals 0 to the equation. So we would have 0 equals 2 to the exponent of x. And we solve for x. Okay, and in this case we would have x as undefined. Okay, there's no number that we can put there that would give us the value of 0. Okay? That's how we know there's no zeros for that graph. And finally, the last one, we have here an infinite number of zeros. Why is that? Okay, Lyndon, go.
We have an infinite amount of zeros because it's where the sign is, it's every 180 degrees, it passes the x-axis.
Very good, yeah. So every 180, so we see here, actually, sorry, every 90, no, every 180, my bad, it's so small, but yeah, every 180 we're going to pass, okay? So we have, this goes on infinitely, so we have an infinite number of zeros. What about our y-intercept here? Eric, y-intercept.
Sorry, I can't speak it in English.
It's okay. X equals, what value of x is y0?
I can't speak it in English.
Okay, then don't worry, we'll come. Somebody else? Help them out? Yeah.
X equals 0.
Yeah, it's x equals 0. Good. Sorry, y equals 0. My mistake. And there's only one. There's only one y-intercept, right? Because there's only one y-axis. Crosses that axis at y equals 0. Next is determine the intervals of increase and the intervals of decrease for each parent function. So intervals of increase is, remember, reading from left to right. When is the graph moving up or the y values becoming more positive? Okay, so we're going to quickly go through these, and then I'm going to give you a chance to copy down the answers. So this one, the interval of increase would be from negative infinity to positive infinity. Okay, this one, interval of increase. Amber.
Can you repeat that? Sorry.
Yeah, when is the y values going up? So when do you see like a positive slope on this graph? Here.
From 0 to the negative infinity.
Close, from 0 to positive infinity,
Oh.
right? Because you're reading it from this direction, from left to right. So from 0 to positive infinity, we're going up. Good. And an interval of decreasing would be from negative infinity to 0. We're going down. All right, Ramon, what about this one? Interval of increasing.
1 to positive infinity.
No. So 1 to positive infinity. So you're saying from here, there's 1, this way, you're saying the values are going up.
Oh, there's actually none.
There's none, yeah, how come?
Because it's asymptote keeps going down.
You're right, there's an asymptote there, but I wouldn't say that's the reason.
Like it keeps decreasing.
Yeah, so if you read it from anywhere on this graph, reading from left to right, it's always going down. Okay, so even though we're really high up here, we're still heading down. Heading down, heading down. Okay, so intervals of increasing on this graph would be none. Intervals of decreasing on this graph, Ramon.
1 to.
No, there's nothing special about 1. Nothing is happening. There's no direction change. In terms of intervals of increasing or decreasing, nothing happens at 1. When are these values going down? So if I'm reading this way, okay, Ramon, is it going down? Is it going down?
Yeah.
Yeah, it's going down. The y values are becoming less and less and less, right? Now I go back to 0. Remember, I never touch 0. I'm all the way up here. Am I going down? Am I going down? Yeah, so your interval of decreasing then would be from negative infinity all the way to positive infinity. Okay, so it's the whole graph. It's always decreasing, this graph. It's a pretty depressing graph, all right?
But if
Yes.
it doesn't hit 0, wouldn't it mean that it's from and not including 0?
Yes, yeah, 0 is undefined, this graph, you're right. But for the function itself, where the function is defined, so not including 0, it's always decreasing,
Oh, okay.
okay? This graph here, Gennaro, interval of increase.
Interval of increase, 0 to positive infinity,
Good. Interval of decrease?
negative infinity to 0.
Excellent. Very good. This graph here, Kevin, in the middle.
0 to infinity.
Very good. Increasing and decreasing?
There's no
Good. It's always increasing. Very good. Nicholas, this graph. Increasing?
Yeah. Increasing is negative infinity to.
Good. And this one, toughest one. Philip.
I'm not sure.
Okay, you gotta listen then. You gotta pay attention. Because everybody should know this. Daniel.
Of increase?
Yeah.
Oh, negative infinity to 0. It just keeps going.
No.
Oh, because it's.
When is it increasing? When are the y values going up? I want to help him out.
-1 positive 1.
No. I know you're thinking the range, Nicholas. You're thinking the range. I'm thinking the interval of increase or decrease. Jesse.
270 degrees to 90 degrees.
From 270 to 90?
Yeah.
It's increasing? So you always read from left to right. So 270 to 90, you're going right to left.
Negative 270.
Negative 270? 0 to 90, yeah, it's definitely increasing. You're right.
Okay, negative 270 then.
No, negative 270 is over here.
Negative 90.
Yes.
And every 360 degrees.
Yeah, that's right. So, all right, we got to look at this one. A lot of people didn't get this one. Okay, so we can see from this point here, which is negative 90, right here, negative 90 degrees, all the way to this point here, which is positive 90 degrees, we're increasing. Okay, so my interval of increase would be from negative 90 to positive 90.
Excuse me for this interruption. Please take the attendance for second period. Thank you.
And then that would repeat itself every 360 degrees. Okay? And then decreasing would be whenever it's going down. So from negative 270 to negative 90. From 90 to 270. Okay, and repeating. All right, it's actually repeating itself every 180 degrees because there's 2 intervals of increase between each 360 degree domain. Any questions about that? Luigi?
Can you write down for the last one just to see like how we would write it down? For
Sure,
the intervals?
sure, I'm gonna show that right now, yeah. Okay, so we've covered up to here for all of our graphs. Okay,
So the paper's missing sine x for us.
Yeah.
is it on the back?
No.
Okay, so you're gonna make it. Okay, so just add on to the table where you can. Actually, if you want to just replace the first one, f at x equals x with sine x, just because that's, yeah, f at x is a relatively easy function. You might want to have sine x as your neat one. So you might want to do this, okay? So this is the handout I gave you. You might want to do this. Okay, or on maybe this function here. You might want to change that. Okay, we know this function looks like this, relatively easy. You want to have sine x maybe written out nice and neat. Okay? So you guys will have a chance to copy all this down tonight. If you want to review the video, I'll make sure the video is up. But the question was, how do I show the intervals of increase? So this is what it looks like. So here's all the ones we know. Negative infinity to infinity, none, 0 to infinity. This again is going from left to right. Keep in mind, guys, these are both x coordinates. I know you're used to kind of thinking as the first one is x and the second one is y. That's not the case here. This is a range for x values. Okay? So it's from 0 to infinity. This is the interval of increase for this graph. 0 to infinity. Okay? 0 to infinity, I'm increasing here. 0 to infinity, I'm increasing here. These are both x values. Okay? So here and here, these are x values.
So are they with the brackets? I can't really see.
Sorry?
Are they in brackets?
Yeah, they look like that. Yeah. Okay?
So it's just like coordinates?
Yeah, it's like coordinates, but that's what I'm kind of highlighting is they're both x values.
Can you like zoom in on your camera?
So the way they've written the interval of increase for the sine function is they're saying 90 degrees where k is all real numbers of z. So they're increasing k. So they're saying every 90 degree intervals this is happening. Okay, so from 4k minus 1 to 4k plus 1. If you don't understand this or don't want to write it this way, you can just write it out. The intervals between negative 360 and 360 and then put a dot dot dot. So for intervals of increasing then that would be from negative 360 to negative 270 comma this is a comma increasing from negative 90 degrees to 90 degrees, comma, and finally 270 degrees to 360 degrees. Okay, that's what you could write for intervals of increase for the sine function. All right? So I'm just writing each interval that it's increasing here. Negative 360 to 270, negative 90 to 90, and negative 270 to 360. And then you do the same thing for decreasing. Negative 270 to negative 90, 90 to 270.
So every 180 degree up.
Right. Okay, we're going to go through a few of the other characteristics of these functions, and then we'll go through the examples. All right, location of discontinuities and asymptotes. So that is, where are there any holes or gaps in the equation? So here, are there any discontinuities? No. So here we would say none. Discontinuities? None. Here, any discontinuities? Yes, Kevin.
X equals 0 and y equals 0.
Very good. Discontinuities at x equals 0 and y equals 0, and for good measure they put in x equals 0 again. I don't know why. Okay, any discontinuities on this one? Luke? Any gaps or holes? No, none. Okay. Oh, they put, location of discontinuities and asymptotes. So they're saying there's a discontinuity and an asymptote at x equals 0. Not sure why they didn't do the same for y. Discontinuities, no, there's none here. Although it doesn't cover the entire domain of the graph, there's still no discontinuities. All right? So this one here, any discontinuities or asymptotes? Philip. X equals 0 is this line here. Good. Y equals 0 is this line. So there's a horizontal asymptote. So there's no discontinuities, but there is a horizontal asymptote. Okay, and last one, Tatoni. Any discontinuities or asymptotes? No, there's none. Good. All right, zeros we talked about. So where the y value is 0. Y value 0 is 0. Y value 0 is at 0. Y value hits 0, never. So there's none. Y value hits 0, it hits at 0. Y value hits 0 at 0. Y value hits 0, never, because there's a horizontal asymptote here. So there's none. And where does y value hit 0? It hits at 0, it hits at 180, it hits at 360. Okay? So they're saying 180k. Every 180, it's going to hit 0. So every multiple of 180, where k is a real integer. Y-intercepts. So where is the x, where does the function cross the y-axis? So when x equals 0, crosses at 0, crosses at 0. Crosses the y-axis, never. Crosses at 0, crosses at 0. Crosses at 1. Okay, there's the value of 1 right there, the y-intercept. And crosses at 0. So we did those two together. Finally, symmetry. Let's talk about that a little bit before we go here. Okay. So when we're dealing with symmetry, okay, so there's two types of